Okay, since we have finished the polymer physics and properties part before the midterm exam, let's start the next part, polymer synthesis, how we make the specific polymers. So we can differentiate, like we can categorize the polymer synthetic methodology by mechanism, by type, and by bond. So by mechanism, there are mainly two different kinds, step growth and chain growth polymerization. By type, similar concept, condensation and addition polymerization. By bond, there's radical and ionic. I mean, we don't know what these are specifically, so we'll learn about each of these type of polymer synthetic methodology soon. So mainly we'll try to compare these two polymerization methods, step growth or condensation and chain growth or addition polymerization. What are their features and what's the difference and the common features between these two different kinds of polymerization method. So I mean, since we cannot really understand what this means, so let's just move on and let's get back to this slide later again after we learn about these two specific polymerization method. So let's move on and try to learn first about step growth polymerization. So the step growth polymerization is also called condensation polymerization. The reason why is that when you basically make polymer chains, long polymer chains, you need to connect each monomer unit, right? And during the connecting the monomer unit, condensation reaction is basically occurs during this step growth or condensation polymerization. That's why we call it either step growth or condensation polymerization. So I just mentioned that by making long polymer chains, we are basically using condensation reaction. So we first need to understand what condensation reaction is. What is condensation reaction? So you might remember this from organic chemistry class, right? So the definition of condensation reaction is basically the reaction between organic base and organic acid. And also, so let's first consider what these organic base and acid are. So organic base are generally referring the alcohol or amine, and organic base refer to the carboxylic acid or acid chloride. So basically, we are reacting these two different kinds of organic compounds, and usually small molecules such as water are eliminated during the condensation reaction. Let's see an example of condensation reaction. So let's consider a reaction between acetic acid, a kind of carboxylic acid here, and ethanol alcohol. Okay. As you all remember from organic chemistry class, the reaction between acetic acid and ethanol is quite clear, right? We form basically ester. Here is the ester group, and we also eliminate basically water molecules. So similarly, we can also react amine and carboxylic acid. Okay, and it's also very common reaction, right? You might remember from organic chemistry or biochemistry class, right? You form by reacting amine and carboxylic acid, you can easily form amide group. Okay. So if you can connect, for example, this is not really a polymerization reaction, right? But if you can form polymers using this kind of ester forming or amide forming reaction, then you can form basically polyester or polyamide, right? So for example, if you make polyester or polyamide, you are basically using this kind of condensation reaction between these two different chemical functional groups. Okay. So if you look at these two examples, the product ester, for example, ethyl acetate or this amide is not polymer. right? The reason why is that the uh, basically the reactants only have one functional group, right? Here is carboxylic acid, here is OH group, hydroxy group, amine, and carboxyl group, right? When they react with each other, they form ester or amide, but not polymers, right? If you want to produce polymer using this kind of condensation reaction, you can easily understand that you need more than two reacting groups. Okay, so we basically denote the number of reacting groups inside of monomer as functionality. Basically what I mean is that we need at least bifunctional or multifunctional monomers to make polymers using these kind of condensation reaction. So let's see an example. Here shows the reaction between diacid. Basically, there are two carboxylic acid group in a monomer. The reaction is between diacid and diol, two hydroxyl group here. Okay, when they react with each other, they form ester group here. Okay, but on the both ends of this product, we still have carboxyl group and hydroxyl group, right? They can react with diol or diacid continuously, right? And then you can add each monomer at the end of this ester and basically forming long polymer chains. Okay, that's why we need at least two functionality for monomer if you want to make polymers using condensation reaction. Okay. So as I just mentioned, functionality is defined as the number of functional groups in a monomer. Okay, so if you have bifunctional monomers such as in this example diacid and diol, you can basically form linear polymers, right? Because the product will have functional groups at the end, right? At both ends, and you can connect monomer, something like this. Basically, we are forming linear polymers. If you have monomer with more than three functional groups, for example, we have some kind of monomer here. Let's say we have three functional groups. Okay, then we can connect with another monomer, something like that, and continuously. Then you'll basically form network type polymers, right? Such as like a network, such as like the fishnet, right? Alright, so now we know what functionality is and what kind of functionality is required to make polymers using condensation reaction. Okay, so if you look at the general polyesterification reaction, basically forming polyester using diacid and diol, let's say that we react diacid n moles of diacid with n moles of diol, right? And basically we can form linear polymers, right? Basically with removing some amount of water. Okay. If you describe this polyesterification or just polycondensation reaction using some kind of picture, you can easily see that as the reaction goes, right? As the reaction goes, each monomer, any monomers inside of this reaction vessel can react with each other, right? With another monomer with different functionalities, right? So these small dots represents the each monomer molecule, right? They can just react with each other, forming basically polymer chains, something like that. Okay. So as the reaction proceeds, there will be some of them will be a little bit longer, some of them are a little bit shorter, etc. Right? And you can clearly see from this general polymerization polyesterification reaction that we need basically equimolar amount of each monomer, right? Equimolar mixtures are ideal for condensation polymerization to obtain high yield of high molecular weight polymer. Basically, to form long chain of polymers, we need basically equal amount of monomers with different functional groups. Okay. Let's say that we do not have equal amount of monomers. What would happen? It's not really produced here, but let's say that we have some amount of monomer diacid and some amount of diol. Okay, and let's say that we have more amount of diol compared to diacid. What will happen? Then the problem is if they react with each other, they form like polyester group, and at the end they will have carboxylic acid group here. Let's just denote carboxylic acid as A group, and here they will have like B group, right? And since we have more amount of diol, right, this will have more likely to react with diol with more amount, right? And this A group will react with this monomer. Okay, then what will happen is that the resulting polymers would have diol group here, basically hydroxy group here, and also hydroxy group at this side. Okay. I mean, when we have different functional groups on one hand and the other hand, those polymer chains will more likely to react with another monomer and form a little bit longer chain. But if they have like same functional groups on each end, okay, the chances are lower to form longer chain. Okay, so the further reaction could be blocked. Okay, this is why we need equimolecular mixtures to make longer chain polymers based on this poly condensation reaction. All right, so let's let me show you. Okay, so then how can you solve this problem? I mean, experimentally, to use equimolar monomer would be a little bit difficult, right? Because we try to like use the scale to weigh the amount of each monomer, but there could be an error, right? Because we just basically human beings have to weigh each monomer using scale and just try to mix them together, right? So instead of using equimolar mixture, there will be a better way to basically solve these limitations. That is simply using this kind of monomer, omega hydroxy carboxylic acid. So this monomer have both functional groups on different ends. Okay, on one end they have hydroxy group, and the other end they have carboxylic acid. Okay, so if you react this monomer with each other, then they will form longer chains without worrying about the equimolar mixture of the different kinds of monomer, right? So you can, there are some monomers with this kind of functional groups. Okay, so simply by using this kind of hydroxycarboxylic acid, we don't really need to worry about this mixing two different monomers with the same moles. Okay, we can just simply do the self-condensation reaction by themselves. Okay? So for example, we already know what these are, right? The carboxylic acid and amine group in one molecule, which is called amino acid, that we learned from biochemistry class, right? If you combine multiple amino acid, we easily form like protein or something like that, right? Okay, so this kind of monomer can commonly be used to make long chain high molecular weight polymers. All right, So as we just learned, if you want to make long chain polymers, I mean, you can either use this kind of hydroxy or carboxylic acid molecules with two different functional groups in one molecule, or you can mix two different monomers with equal amount, okay, equal moles actually, and also to make more basically products. You can also use you can just use the equilibrium, which means that if a certain reaction here, the polymerization reaction is reversible. Let's say that this is monomer A, this is monomer B, and if you form polymers, then it could be reversible, right? There will be forward reaction, and also there will be reverse reaction. And if you want to make more products, long chain polymers, you need to basically shift the reaction to the forward reaction. Then what should you do? You can use Le Chatelier's principle, right? You can remove a polymer, right? For example, as you have seen before, in many polycondensation reactions, we are basically removing water as a product. So if you can remove, for example, remove water, such as using like distillation, then you can shift the reaction to the forward reaction, right? Then you can make more products, basically the long chain polymers. Okay. Another feature is since polyesterification is usually slow at room temperature, you can just heat it up, okay, at higher temperature, or you can use catalyst. All right, I'll just skip this part. It's not important. Okay, if I summarize the polycondensation reaction, basically there are two different types. Okay, you can either use two different monomers with two different functionalities, okay, such as diol diacid, diamine diacid, right? Or you can use the single monomer with two different functionalities in it, okay, such as hydroxy carboxylic acid or amino acid to form long chain polymers using polycondensation reaction. Okay. And general chemical structures which we can make using this polycondensation reaction include ester, amide, urethane, and urea. Okay. So basically, as we already have learned, to form polyester, we basically react monomer with hydroxyl group with monomer with carboxylic acid, right? To form amide, polyamide, we basically react amine containing monomer with carboxylic acid containing monomer. Okay. To form polyurethane, we basically react monomer with this isocyanate group and with the monomer with hydroxyl group. To form polyurea, we basically react monomer with isocyanate group with the amine containing monomers. Okay, these are common polymers that we can make using polycondensation reaction. So below shows the examples of these condensation polymers. The first one is the polyamide, right? Basically, you reacting amine containing monomer with carboxylic acid containing monomer. Okay. Similarly, as a number 2, polyester, we basically react diol with diacid. Okay. Third example is urea formaldehyde polymer. Here we react urea basically have two amine group, diamine with the formaldehyde, forming this kind of formaldehyde. This is not really common polymer. Another example include polycarbonate. Polycarbonate is usually used for like the helmet of the motorbike. So to form polycarbonate, the monomers used to form polycarbonate include bisphenol A, which have two hydroxyl group, and phosgene here, basically forming polycarbonate here. Another example include polysulfide, polysulfone, polyphenylene oxide, glucose. Actually, we learned from biochemistry class polyurethane. So these are not really, familiar with to us, right? So you don't really need to memorize all these chemical reactions. Just try to remember the representative ones like polyamide ester and maybe carbonate and urethane. That'll be enough. Okay. Okay. The others are not really common, so we don't really need to memorize them. One thing to note is that for most of the polycondensation reaction, we basically have product water. Okay, we basically need to remove water as another product to basically to shift the reaction to the fourth reaction. Here HCl, NaCl. There are some small molecules removed. This is not really minus. This is an exception. But if you look at the number 9, the formation of polyurethane, there is no removal of any small molecules. Okay, so I mean, for polycondensation reaction, it is not necessarily required to have this small molecule elimination. Okay, there could be exception. Okay, so now we learn the basic information about the polycondensation reaction or step-cross polymerization. So, as a next step, here shows the Carrodus equation. I don't know what that is. Carrodus equation basically indicates how long, how large molecular weight polymers can we achieve using this step growth polymerization. I mean, we learned that if you use, for example, omega hydroxy carboxylic acid as a monomer, we can make long polymers, right? Using polycondensation reaction, or you can use equimolar monomers, right? I mean, how long or how large molecular weight can you achieve? Okay, that answer can be found in this Carrodus equation. Okay. So Carrodus equation basically shows us the simple relationship between xn bar. Xn bar means number average degree of polymerization. Okay, so you remember the number average molecular weight, right? It's kind of average, right? So degree of polymerization means how many monomers are connected in a polymer chain. Okay, so if the number average molecular weight of a certain polymer is mn bar, then the mn bar is equal to number average degree of polymerization xn bar times the molecular weight of the monomer. xmo basically refers to the molecular weight of the monomer. Okay, so this xn basically means how many monomer units are contained in a polymer chain in average. So basically this equation basically shows the relationship between this number average degree of polymerization and P. P is extent of reaction, how much reaction has proceeded, right? Okay, so since the P is extent of reaction, P is defined as the probability that any functional group present initially has reacted, right? So at the beginning of the reaction of this polycondensation reaction, there will be many functional groups, right? Each monomer have at least 2 functional groups, right? And after some time t, some of them would have reacted with each other, forming longer chains, right? Okay, so I mean, since P is the extent of reaction, okay, if those reacted functional groups have reacted, then P will be same as the probability that any functional group has reacted, right? Probability of the reaction, right? Okay, so this P extent of reaction, or we can just say it's just a conversion, degree of conversion, can easily be written in terms of the number of moles. Let's say that we have the N0 is the number of functional groups at the beginning of the reaction. Okay. Then N0 here is the number of molecules present initially, basically number of monomer molecules, right? Then if there are N0 number of molecules, then the number of functional groups, if you are only considering bifunctional monomers, then the number of functional groups would be 2 times N0, right? Okay. And N is defined as the number of molecules remaining at time t. Okay. After some time t, there will be some number of molecules. Here, molecule means monomers or the long chain polymers, etc. Right? Okay. So if you define N0 and N as shown here, P can easily be defined as the number of groups that have reacted at time t divided by number of groups present initially. It's obvious, right? Because the P is the probability of the reactive functional groups, right? So since the initial amount of molecules are N0, initial amount of groups, here groups, the functional groups would be 2 times N0, right? Okay, and the number of functional groups that had reacted at time t would be N0 minus N times 2, right? As one reaction occurs, then 2 functional groups disappear, right? OH and COH, something like that, right? So if you divide 2, then P is equal to N0 minus N over N0, right? Okay. So if you rearrange it in terms of the N0 over N, then you can get this expression N0 over T is equal to 1 over 1 minus P. Okay. Okay. Then, how can you express this number average degree of polymerization xn bar in terms of P? Okay. So this one basically represents the average length of the polymer chains, right? Some of them will be a little bit longer, some of them will be a little bit shorter, right? We want to define the average length of polymer chains at time t. Okay, they can also easily be defined. Number average degree of polymerization is actually number of molecules present initially divided by number of molecules remaining after time t. What does this mean? This means that let's say that we had initially 100 monomer molecules, okay, and after time t, okay, after some time, we just counted the number of molecules, number of polymer chains, and the counted polymer chains were, for example, like 5. This is monomer, number of monomer molecules, and this is number of polymer chains. Then you can easily calculate the average polymer chain length. Average chain length is 20, right? Okay. Some of them might be a little bit longer, like 23. But some of them might be a little bit shorter, like 18, 17, something like that. Anyhow, the average molecular chain length would be 20, right? How could we calculate this 20? We just simply divided 100 by 5, right? That is basically same expression as N0 over N. Okay? So, the number average degree of polymerization is actually N0 over 10. And N0 over 10 was 1 over 1 minus P. This is it. Okay? This is called Cardo's equation. Okay? This clearly shows the relation between number average degree of polymerization and conversion. Okay? Or the extent of reaction. Okay? Very simple, right? Very simple result actually. Okay? So, if you just plot this Cardo's equation, let's move on to the following slide here. Here, this one. If you plot number average degree of polymerization as a function of P, Okay, as we just have seen, this xn bar is equal to 1 over 1 minus p. So, and p is degree of extent of reaction, okay, which means that p is between 0 and 1. Okay, so when p is 0, xn is just 1 here. As the p increases up to 1, it clearly increases something like this, right? Let's say that p is like 0.5, then xn is 2. P is 0.9, then xn is 10, which means that the average length of the polymer chain is 10, right? 10 monomers are combined with each other. 0.99, 100, 0.999, 1000, 0.9999, 10,000. Which means that if you want to make really long chain, really high molecular weight polymers using polycondensation reaction, what you need to do is you need to achieve the conversion or extent of reaction almost approaching 100%. Okay, then you can get really high molecular weight polymers. Okay? Okay. So this is Cardo's equation. Let's move on. Here shows another equation which is called generalized Cardo's equation. So we are basically using the same definition of P, but here P was what? Number of groups that have reacted at time t divided by number of groups present initially, right? In previous slide, right? Here we are going to. I'm doing. Oh, sorry. This is hide. I don't know how can I do that. Okay, so this is I'm going to use this definition. Okay, but in deriving this equation, we just consider the monomers with two functional groups. Okay, bifunctional monomers. But if we have like monomers with more than two functional groups, what would happen? Okay, so let's say that small f, we define small f as the number of average functional group per monomer. Okay, maybe one monomer have two functional groups, but the other monomer might maybe have 3 or 4 functional groups, right? Then P can be calculated by this equation, right? This in the nominator is same, right? Number of groups that have reacted at time t, right? Because as the reaction proceeds, only 2 functional groups disappear, right, for each reaction. Okay, that's why we put 2. But at the beginning of the reaction, the number of functional group would be n0 times f, not 2, right? Because the number of average functional group is denoted as f, right? Okay, so P is a little bit different, right? And since number average degree of polymerization is n0 over n, if you just rearrange it, you can get the relation between xn and P as shown here. Xn is equal to 2 over 2 minus fp. Okay, this is generalized Cardo's equation. And you can clearly see that when f is 2, it becomes the Cardo's equation, 1 over 1 minus p. Okay? Alright, so this Cardo's equation and this generalized Cardo's equation, well, when both monomers are in equal amount. Okay, if it is not, what would happen? Okay, let's say that we are basically reacting 2 different monomers with bifunctional groups, Ra2 and Rb2. Here, A and B denotes the 2 different functional groups. And let's say that we have excess amount of Rb2. One of the monomer is in large amount. Then what would happen to this Cardo's equation? Okay, so here we define another term, small r, which is called reactant ratio, as Na over Nb. This is the definition of small r. Okay, Okay. Then we want to write this Caldas equation again similarly. Alright, N0, number of molecules present initially, would be Na, number of A monomer plus number of B monomer divided by here this Na and Nb denotes the number of functional groups. Okay. Okay. So Na plus Nb divided by 2, because each monomer have 2 functional groups, right? Would be same as N0. Okay. And since we defined R as Na over Nb, so Na is equal to R times Nb. Okay, so we can put this equation into here, Na here, then we can have this expression. Okay, this is N0. Okay, now we want to calculate N, here N, okay, number of molecules remaining at time t. So let's first calculate the number of unreacted A groups. Okay, so initially there were Na functional groups in this monomer. Okay, and if the extent of reaction, the conversion is P, okay, and this amount is reacted amount of A functional groups, right? So if you subtract this, then you can get unreacted A functional groups, right? So if you rearrange it, you can get actually Na times 1 minus P, and since Na is R and B, you can put it here and you can get R and B times 1 minus P. This is the number of unreacted A functional group. Similarly, you can calculate number of unreacted B functional groups, which would be Nb minus here, which is at P and A. The reason why is that B is in excess, okay, excess amount of B, okay. So the degree of reaction would be depends on the smaller amount, which is A, right? So if you rearrange it, if you calculate it, you can get this. Okay, so you calculated unreacted A and B groups. Okay, so if you calculate the N, number of molecules remaining at time t, which would be this plus this divided by 2, since there are 2 functional groups, okay, which is this. Okay, so by definition, the number average degree of polymerization, which is N0 over N, can easily be calculated as this. Okay, so you could easily express the more generalized the number average degree of polymerization. I mean, you can check, right? Let's say that R is just 1. Okay, if the amount of A and B molecules are just 1, then if you put it 1, you can, what you get is 1 over 1 minus P. Okay, Caldas equation. Okay. Okay, so you can check. Have you already seen this, right? So what you got is this one, okay, just before. So let's say that we have like 5% excess amount of diacid molecules. Okay, we are basically, let's say that we are making polyester, okay, and one molecules in large excess amount, and it's only like 5%. Okay, that the reactivity ratio would be 1 over 1.05, which is 0.9524. If you put this R value here, and here, okay, then you can calculate the number average degree of polymerization at conversion of 0.999, which is only about 39. Okay, it's quite surprising, right? When P is 0.999, we could achieve the number average polymer chain length of the 1000, but when there are only 5% large amount of one kind of monomer, then we can only achieve about 40 polymer, average polymer chain length, which is much smaller than 1000, right? Okay. From this equation, let's say that we are achieving like 100% conversion. Let's say that P is just 1. Then if you put 1 here, what you can get is 1 plus R over 1 minus R. Okay? Even we achieve like 100% conversion, if there is like 5% more amount of the monomer compared to other, okay, then the maximum number average degree of polymerization is only 41. Okay, so the equal amount of monomer, or just using hydroxy like two functional groups inside of one monomer, is very important to achieve long chain or high molecular weight polymers. Okay, as you have learned before in polymer properties class, that high molecular weight is very important, right? High molecular weight generally ensures high properties, better properties like high mechanical strength, high thermal strength, etc. So, in polycondensation reaction, the equal amount of monomers are very important. Okay. Okay. Now let's move on to the kinetics of polycondensation reaction. Basically, considering the reaction rate. Okay. So, in dealing with kinetics, we'll assume that the reactivity of the functional group is unaffected by the length of polymer chains, and it is actually experimentally verified. The reactivity of the short, for example, like monomer and the long chain polymers are pretty much the same. Okay, so we are basically assuming that the rate constant is just a constant. Okay. All right. So let's say that we have a polycondensation reaction between hydroxyl group and carboxylic acid group, and the reaction rate of reaction will be the change of the concentration of the reactant, right? So the minus D carboxylic acid, the concentration over dt, or it will be same as minus D OH over dt, right? Because the as the reaction proceeds, one carboxylic acid group react with one hydroxyl group. Okay. First, let's consider the case at which catalyst is not used. Okay, between these two reactions. Okay. In this case, acid group, okay, basically the monomer with the carboxylic acid group in the reaction mixture act as self-catalyst. Okay, it works as a monomer, at the same time it works as a catalyst. Okay, so the reaction rate of reaction can be written by rate constant times the concentration of the monomer, and also since the acid group, the acid monomer is used as the catalyst, the concentration of catalyst should be multiplied again. And since catalyst is itself same as the COH, okay, so we have to multiply as to the power of 2. Okay, and since if you assume that the concentration of the COH monomer and the concentration of the OH monomers are same, equimolar mixture, and let's just denote the concentration as just C. Okay, then if you re-express this rate law, minus dC over dt is equal to kc to the 3. Okay, simple first order differential equation. And if you solve it, you can get this equation, this result. Okay, and if you rearrange it in terms of the n0 over n, which should be same as C0 over C, which is equal to the Carothos equation. Okay. So if you multiply this equation by C0 square on both sides, you can easily get this equation. Okay. So if you look at this, if you plot for example, 1 over 1 minus p squared as a function of time, we can get linear relationship. And the slope is equal to 2kc0 squared, and the slope intersect is 1, right? This is the case when no catalyst has been used. On the other hand, if we use additional catalyst to make this reaction occur, polycondensation reaction, then the rate law is a little bit different. Okay. In this case, since we added catalyst, and this added catalyst is much more efficient compared to the self catalysis of the carboxylic acid group. So the rate of reaction will be equal to the first reaction that we have written here, plus the rate of the two monomers with the catalyst. Here catalyst we use usually acid, so additional acid. Okay. And here, as I just mentioned, the efficiency of the catalysis is much better than the self-catalysis, which means that the rate constant, if you compare the rate constant, this rate constant of the catalyst, kcat, is much larger. So we can basically ignore this part. Then we have some other different reaction constant and the concentration of the monomers. Okay. So as you denote the concentration of hydroxyl group, carboxylic acid group, and hydroxyl group as C, then you get this expression. Okay, simple first order differential equation, and if you do the integration, you can get this relationship. Okay. So the kinetics depends on either we use catalyst or not. Okay, let's move on to the size distribution in linear polymers. So as you do the polycondensation reaction, as you react two different functional groups with each other, you are basically making long polymer chains at high conversion. Okay, but the thing is, creation of these long polymer chains is a random process, so there should be size distribution, right? The reactivity of the functional groups are basically same regardless of the polymer chain length, right? So some polymer at the end of the reaction, some of them would be a little longer, some of them would be a little shorter. There will be distribution of the polymer chains. Okay, so we want to determine this size distribution in linear polymers formed by polycondensation reaction. Okay, so here we'll consider omega hydroxycarboxylic acid as a monomer. This one is monomer. Okay, so general structure is given here. Okay, so as this monomer react with by themselves, then the length of this monomer unit will be longer, right? So here, if I is equal to 1, which basically means it's a monomer. If one monomer react with each other, then they will form like dimer, right? I is equal to 2, something like that. Okay. So when I is 2, which means that there was one reaction, right, between two different monomers, basically I minus 1 ester bond, right? Since there is only one ester bond here. Okay, so if you want to form I length of polymer chains, let's say that we form I different monomer units connected with each other by this polycondensation reaction, forming multiple ester linkage, which means that if we form I monomers combined together, that means there should be I minus 1 ester linkage, right, as shown here. Okay, how can you express this? we'll express this in terms of P, extent of reaction, or the probability of a functional group, okay, of the functional group that has been reacted. Okay, since we want to combine I monomers, the number of monomers combined are I. To do that, what you need to do is you need to make I minus 1 ester linkage, okay, and the probability to make ester linkage is equal to P, right, extent of reaction, and we should do it I minus 1 times, sorry, right, P to the I minus 1, right, and then the reaction should not occur, right, because we want to make the length of the polymer chains as I, right, so the additional reaction should not occur, okay, and the probability that the reaction does not occur is equal to 1 minus P, okay, so which is equal to P to the I minus 1 times 1 minus P, which is denoted as PI, probability that the polyester molecules containing I units. Okay, simple. Okay, right, this is the probability, and if there are n total molecules at time t, the number of total molecules are denoted as n, right, remember, okay, then the number of polymer chains with the I units, which is Ni, number of polymer molecules with length of I, should be equal to total number of molecules times probability, right? So n times Pi, which is equal to n times small p to the I minus 1 times 1 minus P. Okay? And from equation 2, which was the one that we used in deriving Carrod's equation, n was equal to n0 times 1 minus P. Okay, so we'll put this n into here. Okay, then what you get is this: Ni is equal to n0 times P to the I minus 1 times 1 minus P squared. Okay, this is the number of polymeric molecules of length I. Okay, let's calculate also the weight fraction of the polymeric molecules of length I compared to the total molecular weight of the polymer chains. Okay, so the weight of the polymeric molecules of length I should be equal to, this is the number of the polymeric chains of the length I, and the molecular weight of this I chain would be I times M0, right? Because M0 is the molecular weight of the monomer, right? And the total molecular weight would be N0 times M0. Okay? So this is the weight fraction of the I, the polymer chains of the length I, okay? So which is equal to I over N0. Okay? So if you put this Ni into here, you get weight fraction as shown here. I times P to the I minus 1 times 1 minus P squared. Okay? So you got this and also this. Okay, let's move on. Okay. Now we are ready to calculate the molecular weight. Number average molecular weight was defined as this equation, remember, from chapter 3 or 4, right? Okay. So here in this equation, you want to put this Ni, this one, into here. into here, here Ni and here. And in the denominator, the summation of the Ni is equal to just N. Okay. So if you put Ni here, and also Mi, the molecular weight of the I, the length I polymer chains will be equal to Im0. Okay, so if you put and if you do sum, you can get this expression. Okay, And from this sigma, this calculation, that can be easily obtained from this. Okay, I mean here you can get it from this one. So P is the conversion, so which is between 0 and 1. From high school mathematics, maybe middle school mathematics, you remember that 1 plus P squared plus the infinite series, right, equal to 1 over 1 minus P, right? Remember this, right? Okay. If you take the derivative on both sides with respect to P, take the derivative, then you can get this expression. Okay, so you can do it by yourself. Okay, if you take the derivative on both sides of this infinite series. Okay, so you can put this one into here. Then what you get is the number average molecular weight that you can achieve using polycondensation reaction is m0 over 1 minus p. Okay, and number average degree of polymerization is defined as the mn over m0, and we got Carnot's equation, right? Okay, I mean we could derive Carnot's equation in a different way, but using the molecular weight distribution of the polycondensation reaction, we could also get the same result, Carnot's equation. Okay, we can also calculate the weight average molecular weight by definition. We can put the definition, the weight fraction weight here that we got here. Okay, so put it here and you just calculate the sigma. You need to calculate it, and this one can be obtained if you take the derivative of this equation on both sides. Okay, so let's say that we just have the result as shown here. Okay, so if you just use this result, and what you get is weight average molecular weight is m0 times 1 plus p over 1 minus p, and weight average degree of polymerization by definition by this one, and 1 plus p over 1 minus p. And mw, the weight average molecular weight over number average molecular weight, is called polydispersed index. And if you calculate it, since mn is here, right here, this one, okay, if you put it there, you can get the polydispersed index, or PDI, for polycondensation reaction is equal to 1 plus p. Very important. Which means that as you increase the p, which means p is the conversion extent of reaction. So if you p approaches 1, you can get basically polydispersed index of 2 for polycondensation reaction. Okay. Okay. So below shows the number average, the length of the the polymer chains of length I, or the wave fraction. Okay, basically the if you plot this, where is it? These two equation 15 and 16, as a graph, then you can get these two equations. This is from the other textbook, Florida book. It's very interesting, right? The molecular weight distribution of the polycondensation reaction is quite interesting, right? The results are quite simple, right? Quite simple, and we could even see the Carnot's equation, and the polydispersed index is also very simple expression, right? Okay, let's cut. Okay, the final part of the polycondensation reaction, or the step growth polymerization, is on non-linear step growth polymerization. So up to here we have mostly considered the linear polymers, where the functionality of the reactant was 2, right? But if the functionality is larger than 2, then we learn that we form network polymers, right? So let's say that we have two different monomers, okay? And monomer A have three functionalities, and monomer B has two functionalities. Then the resulting chemical structure of the polymers will be something like this, right? It will be connected something like with each other, forming basically network type polymers, such as fishnet. Okay, so the real example include the reaction between triol, which have three hydroxy groups, something like this, and diacid. So if you react with these two monomers, basically they form the 3D network structure. Okay. And that one thing that we need to consider in dealing with the network polymer is that since they are quite largely cross-linked with each other, the resulting polymers are really like hard and insoluble material. So as you react these kind of multifunctional monomers with each other, and if you, for example, experimentally measure viscosity of that polymer solution as a function of time, there is a certain point at which the polymer solution becomes gel. Gel is, I mean, before forming gel, the polymer solutions are just called ZOL, or just soluble melt, simple just liquid. But after a certain point, viscosity increases infinitely, and it forms gel, which is like insoluble material, and there's no flow, and it's impossible to stir the polymer solution. The reason why is that gel is basically 3D network polymers, and it's quite largely cross-linked, so they cannot really maintain this soluble liquid state. Okay. So in this case, this abrupt change point is called the gel point. Okay. And the physical properties of ZOL and gel are quite different. As I mentioned, gel is insoluble and it's kind of solid just. Okay. And from this concept of gel point, and from the knowledge that we have learned so far, especially using the Keratos equation, we can predict the gel point, basically the conversion. Okay, let's do that. Alright, so let's consider a mixture of monomers. Okay, and here we already have seen this before, right? Small f is the average number of functional groups per monomer unit, right? Some of them might be functional group, 3 functional groups. Some of them might be have like 2 functional group or 4, something like that. So the average number of functional group is denoted as F or FAV, average. Okay. Then F times N0 means number of functional groups present initially, right? N0 is the total number of functional groups, right? Total number of the molecules at the beginning, okay? And the number of functional groups reacted would be equal to 2 times N0 minus N, right? Because per reaction, two functional groups disappear, right? So by definition, the P, degree of the extent of reaction or the conversion, is equal to 2 times N0 minus N over N0 times F. Okay? And you can also calculate the number average degree of polymerization, which is equal to 2 over 2 minus P times F. Okay. So you can clearly see that if F is, for example, 2, if average number of functional groups is 2, then you can get Keratos equation 1 over 1 minus P. Okay, from this equation. Okay. So we got the a little bit more general Keratos equation when the number of functional groups are larger than 2. Here, we now define this gel point. Okay, so here in the gel point, the viscosity of the polymer solution increases suddenly, like abruptly, okay? At which we can pretty much assume that at that point, polymer molecular weight or the number average degree of polymerization approaches infinite. The reason why is that since it approaches a really large number, that's why the viscosity increases infinitely, and also it basically forms the largely cross-linked network structure. Okay. From this characterization, kind of characterization, if the number average degree of polymerization is infinite, which means that this part 2 minus p times FAV is equal to 0, right? This one is equal to 0. Then you can easily calculate p, which is equal to 2 over f. Okay? So if you have the information about the monomers, if you have the information about the average number of functional groups per monomer molecule, then you can easily calculate the gel point. At what conversion you can get gel point. For example, let's say that we have 3 different kinds of monomers, and which is stoichiometric mixture, 2 moles of diacid, so there are 2 functional groups, 1.4 moles of diol, 2 functional groups, 1.4 moles of triol, 3 functional groups. Okay, so if you can check that this is stoichiometric mixture, right? 2 moles of diol, 2 times 2 is equal to 4, right? And here 1.4 moles of diol, 1.4 times 2 is equal to 2.8, plus 1.4 times 3 is equal to 1.2, which is equal to 4, right? Same as here, okay? Anyhow, there are 3 different monomers, okay? Then we can calculate the average number of functional groups, as shown here, right? Which is equal to 2.1, okay? Since you have the information about the average functional groups, then you can calculate the gel point, okay? It's very simple, right? If you calculate it, what is the number? 2 over 2.1 is equal to 0.95. So when p is equal to 0.95, about 0.95, it basically approaches gel point, infinite number average degree of polymerization. Okay, so you can check if, for example, if the F average is 2.2, then you even get the gel point between like 0.9 and 0.95. Okay. So next shows some examples of network polymers. And network polymers are basically thermoset, right? Because after you form crosslinks, you cannot really reverse that reaction, right? If you heat the thermosetting network polymers, you can just degrade the polymers, thermally degrade. So network polymers are basically crosslink structure, very high strength, mechanical strength. Okay. So after you form crosslinks, then you cannot really melt again because it is thermoset. There are a few examples of network polymers. One of them is phenol formaldehyde resin. Okay, so you know what phenol is here. This one is phenol. Okay, and formaldehyde can react with each other. And when they react with each other, this formaldehyde can be connected to the phenol at this ortho or para position. Okay, basically there are 3 reacting sites. Okay, 3 reacting sites, and this monomer can react here, here, or here. Okay, so depending on the reaction condition, different types of catalyst or different amounts of the reactants, it can either form like linear chain or the more like network type chains. Okay, so the product name For this one is called novel log, and this one is called resol. Okay. Another example is melamine formaldehyde resin. Okay, same formaldehyde monomer here, and this one is called melamine. Okay, so the chemical structure is, if you look at the chemical structure of melamine, they have 3 amine groups here, basically 6 hydrogen atoms, and those 6 NH group, okay, 1, 2, 3, 4, 5, 6, can be used as the linking site for formaldehyde, right? There are 6 linking points. Here there were 3 linking points, right? Linking reaction site. Here there are 6 reaction sites. Okay, so it can form cross-link network polymer. Another example is epoxy resin. You might be familiar with epoxy. It's kind of adhesive, right? It's very strong adhesive, right? Yeah, for epoxy resin, the monomers used epichlorohydrin. Chemical structures are here, and bisphenol A. Okay, this one. Okay, if they react with each other, they form this structure. Okay, and if they if this chemical react with the curing agent, which is usually the multifunctional amine or acid or anhydride, so these structures with here, this functional group here, they can connect with these multifunctional amines and basically forming network structures. Okay, so this is pretty much it for step growth polymerization. So let's move back to the first slide of this chemical polymer synthesis. In summary, here, so we just finished about the step growth polymerization. So we know that the growing chains react with each other because all the chains have functional groups. Okay, and polymers grow to a high molecular weight at a slow rate because each monomer can, any chains have the functional groups. Okay, and high molecular weight is formed at the end of polymerization, right? You remember this graph, right? For Mn, or for number average degree of polymerization, this is a conversion. The step growth polymerization follow this kind of curve, right? At really high conversion, you can achieve high molecular weight. So we need long reaction time if you want to make long chain or high molecular weight polymers using step growth or polycondensation method. Okay, so in the next lecture we'll learn about this chain growth or the free radical polymerization.